Welcome to the debate. What if your smartphone knew you were going to develop type 2 diabetes maybe 3 years before your doctor did?
That is the big question, right? And what if it didn't even need a blood test? Like just a quick scan of your eye or literally just the way you walk to see this massive biological storm brewing inside you.
Exactly. And today, that isn't science fiction anymore. It's actively happening in clinics right now. And it really forces us to rethink how we approach a massive category of illness.
Yeah, because usually, when we picture a medical crisis, we think of something super visible and sudden. A ruptured appendix, right, or a fractured femur. The physiological sirens go off and our healthcare infrastructure just springs into this acute care mode.
But the biggest threats to global health aren't sudden at all. We are dealing with a totally silent epidemic of metabolic diseases. So we're talking about type 2 diabetes, clinical obesity, metabolic syndrome.
Right, and non-alcoholic fatty liver disease, NAFLD, which is just skyrocketing globally.
Oh, absolutely. And these conditions, they don't just strike overnight. They are these slow-moving cascades. They start with microscopic, interconnected disruptions in, how your body processes glucose, how it stores lipids.
How it manages inflammation, yeah.
Right. And they brew for years completely undetected until the damage finally erupts into a heart attack or a stroke or total kidney failure.
And the real tragedy of that timeline is that by the time those overt symptoms finally appear, the structural damage to the vascular system is largely permanent. That preventative window, which was open for a decade, has just slammed shut.
It really has. Which brings us to the core of our discussion today, because we are witnessing the integration of artificial intelligence and machine learning into metabolic disease prediction. It represents this massive theoretical shift from reactive firefighting to proactive guardianship.
Right. But the central question we really have to grapple with here is this: does the global rollout of AI in healthcare represent a universally scalable triumph that will actually prevent these diseases?
Or, and this is the flip side, do foundational flaws in the technology, specifically fragmented data systems, representation blind spots, and that infamous black box problem, just fundamentally compromise its utility?
I'd argue it's probably the defining medical technology question of our time.
I completely agree. And our analysis today is rooted strictly in the current literature, documenting AI's deployment in global metabolic health. We're looking at everything from massive hospital networks in New York to, rural health outposts in sub-Saharan Africa.
Right.
So I'm taking the position that AI's unprecedented ability to synthesize multidimensional data sets, ranging from your genomic sequence all the way to the raw data streaming from your smartwatch, offers a highly accurate, inherently scalable solution to avert metabolic crises before they even happen.
And I will be taking the position that the mathematical promise of this technology is severely undercut by physical realities. I'm looking at deeply entrenched data silos, algorithmic blind spots, and opaque, unexplainable models that clinicians on the ground simply cannot trust with human lives.
Well, let's just dive right into the actual predictive mechanics of these models, because the sheer scale of what machine learning achieves today is staggering, especially when you compare it to the traditional human-built risk models we've relied on for decades.
You mean legacy frameworks like the Framingham Risk Score for cardiovascular disease or Finland's FINDRISC diabetes?
Exactly. What are those, really?
Well, they're essentially static calculators. You plug in age, weight, blood pressure, family history, and it just spits out a generalized risk percentage.
Right, and they're highly limited because human biology just isn't a linear equation. Those static formulas fundamentally miss the nuanced, non-linear interactions happening across billions of cells.
No human doctor can process that many variables at once.
Exactly my point. Machine learning, specifically deep neural networks, are uniquely equipped to spot these invisible correlations. We are taking massive data sets, millions of patient records, genetic markers, continuous lifestyle habits, even sleep architecture, and letting the algorithm find the physiological threads that no human has the cognitive capacity to see.
Look, I don't dispute the mathematical superiority of a deep neural network over a paper calculator. That's obvious. But we have to ground this theoretical math in clinical reality.
But the clinical reality is already yielding incredible results. Take a look at the 2023 study published in The Lancet Digital Health. Google's DeepMind algorithm successfully predicted type 2 diabetes up to 3 years in advance.
Wow, 3 years?
3 years! And it didn't do this by demanding expensive, specialized blood panels. It did it by analyzing simple retinal fundus images, literally just photographs of the back of the eye.
I think it's worth explaining why the eye is so crucial there, actually, because it's not magic. The retina is literally the only place in the human body where we can directly and non-invasively observe the microvascular system.
Right, you can see the blood vessels.
Exactly. When someone's blood sugar is chronically elevated, it damages those tiny blood vessels way before the major organs start failing.
And the AI is detecting microscopic vascular changes that a human ophthalmologist would never, ever catch. The model achieved an area under the curve, or AUC, of 0.91.
Which is incredibly high.
It's massive. For context, an AUC of 1.0 is a perfect oracle, right? And 0.5 is a random coin flip. Hitting 0.91 means it's correctly identifying 91% of at-risk individuals. And the best part? This approach is globally scalable.
Scalable how, exactly?
Well, look at China. Diabetes prevalence is skyrocketing there, right? Tencent's AI is processing WeChat health data to flag pre-diabetes. It's literally looking at anonymized step counts and daily meal logs. And we don't even need to centralize all this data to make it work.
Ah, you're talking about federated learning.
I am. Think of federated learning like a traveling medical student doing rotations around the world.
Okay, I'm tracking.
Imagine this student visits a hospital in Paris, then a clinic in Rio, then maybe a rural outpost in Kenya. Now, the student is absolutely forbidden from taking any patient's physical chart out of the building. The data stays locked in the vault, completely respecting international privacy laws like the GDPR.
Right, the raw data never moves.
Exactly, but the student can take the clinical knowledge they gained from treating those patients. They update their internal understanding of the disease, and they carry that insight to the next hospital. In AI terms, we send the algorithm to the data. It updates its mathematical weights locally, and only those upgraded weights travel across the network.
Okay, your traveling student metaphor is brilliant, I'll give you that. But it actually highlights the exact problem I have with this whole global deployment theory.
How so?
It completely ignores the infrastructural reality of global healthcare. Let's run with your analogy. The student travels to Paris and reads perfectly formatted, digitized electronic health records. Great! Then the student travels to Rio and finds a completely different software system that codes diseases entirely differently.
Well, data standardization is a known hurdle, sure.
But wait, it gets worse. Then the student goes to Kenya and finds that the clinic doesn't use digital records at all. Everything is handwritten in a paper ledger. What does your brilliant student learn then?
They learn what they can from the available.
High-tech AI fundamentally assumes a foundational level of data harmony and digitized hardware that simply doesn't exist globally. Europe's health systems are hopelessly fragmented. You contrast that with China's unified systems, which are structurally incompatible with Western formats anyway. And in a lot of lower-income countries, the digitized data isn't just formatted differently, it just literally doesn't exist.
Okay, but we're not relying solely on traditional hospital IT infrastructure anymore. That's the beauty of edge computing. AI is bypassing those legacy hurdles entirely through device portability. We don't need massive centralized hospital servers.
You're banking on consumer tech then?
Exactly. Think about continuous glucose monitors. They are streaming real-time metabolic data directly to smartphones, Apple Watches, Xiaomi bands. The footprint of medical data collection is shrinking dramatically. Look at the Mayo Clinic's EchoNose platform.
The portable ultrasound one?
Yes! They aren't waiting for a multi-million-dollar fiber optic hospital network to be built. They are bringing portable echocardiography tools directly to remote Latin American Amazon outposts. And the AI analyzes the ultrasound video locally on the device to detect fatty liver disease with biopsy-level precision.
Right, but that still requires the patient to have a smartphone, a wearable device, and a reliable telecommunications network to support it.
I mean, yes, we have these 5G-enabled telemedicine platforms scaling to millions of users, sending personalized health nudges, but beneath that very impressive tech veneer, the underlying data is profoundly siloed.
But Edge AI processes it on the spot.
Sure. But if a patient's wearable data is trapped in an Apple ecosystem and their genomic data is sitting in some private biobank and their actual clinical history is fragmented across 3 different hospital records, the AI cannot form the holistic picture it needs. Federated learning only works if the local data the algorithm visits is comprehensive. When it's not, the AI is functioning on fractured intelligence.
I hear ya. But the data doesn't actually have to be perfectly comprehensive to be clinically useful. Even analyzing partial data, like just that retinal scan in isolation, yields that 0.91 accuracy. We are still catching things we would have completely 100% missed otherwise.
Okay, but catching a pattern mathematically isn't the same as practicing medicine. And that brings us to what I consider the absolute ceiling for this technology's adoption.
Which is,
The black box trust deficit. You can have an algorithm that boasts incredibly high accuracy, but if the clinician looking at the screen cannot explain the biological rationale behind the prediction, they simply cannot use it. Let's look at the multiomics trial published in Nature Medicine in 2025.
oh, the multiomics trial, yes.
Right. And before we get into the results, let's just define what they actually did here, because it's a monumental data effort. Multiomics means they didn't just look at DNA. They integrated genomics, which is the genetic code, proteomics, the proteins actively being produced, and metabolomics, the chemical footprints left behind by cellular processes.
They basically mapped the entire cellular environment.
Exactly. They fed all these different layers of biological data into massive neural networks, and they predicted the progression of non-alcoholic fatty liver disease with an astounding 88% accuracy across 10,000 patients from the US, India, and Nigeria.
I mean, it's a genuine technological marvel.
It is. It really is. But the output is a black box. The network is so incredibly complex with millions of hidden layers and weighted connections that the researchers themselves literally can't tell you exactly which combination of proteins and genes led to the final prediction.
Well, but the prediction is accurate.
But put that tool in the hands of a doctor. The machine says, hey, this healthy-looking patient will develop severe liver disease in 2 years. Put them on aggressive pharmacological intervention right now. A doctor cannot prescribe a heavy medication if they can't explain to the patient why they need it. It breaks the fundamental requirement of informed consent.
I see the ethical dilemma, but
In fact, the literature already shows doctors in Nigeria actively balking at opaque AI predictions for this very reason. If the AI is a black box, the clinical trust is broken, and the tool is useless.
See, I am really not convinced by that line of reasoning because I think it totally misunderstands how medicine actually operates right now. I completely challenge the premise that absolute algorithmic transparency is required for clinical utility.
Really? How so?
Let's look at pharmacology. We prescribe countless pharmaceutical drugs where the exact biological mechanism of action is incredibly murky or in some cases completely unknown. Look at acetaminophen or lithium for bipolar disorder.
Okay, fair point on lithium.
Right? For decades, we didn't fully understand how they worked in the brain, but we prescribed them anyway. Why? Because rigorous double-blind clinical trials proved their efficacy and their safety. We knew they worked even if we didn't know exactly how.
But that's different.
Is it? Why should an AI model be held to an impossible standard of perfect mechanistic transparency when a biological intervention is not? If an AI model is rigorously validated in clinical trials and consistently prevents metabolic collapse, its empirical success justifies its use. Efficacy trumps the black box.
I come at it from a very, very different angle. A drug's mechanism might be partially mysterious, sure, but its physiological effects are localized, they are measurable, and they are biologically uniform. A drug interacts with human chemistry. An algorithm's mechanism isn't biological, it's strictly statistical. It is actively looking for patterns, and it is entirely capable of incorporating spurious correlations.
What do you mean by spurious correlations? Give me an example.
I mean, the AI might predict a higher risk of liver disease, not because of the patient's actual cellular biology, but because the algorithm noticed that patients scanned on a specific, older ultrasound machine at a specific hospital tend to be sicker.
Ah, so it reads the machine's watermark or image grain.
Exactly. It correlates the machine's image resolution with the disease. If we don't know how the AI is weighting the variables, we don't know if it's actually practicing medicine or just recognizing administrative patterns.
Okay, that's a fair concern with early iterations. But we aren't flying entirely blind anymore. The field of explainable AI is actively breaking open that black box. The newer systems don't just spit out a generic risk percentage anymore. They perform variable isolation to highlight the specific modifiable factors driving the prediction.
Wait, so it actually points the doctor to the specific data points it used?
Yes, exactly. It can quantify the inputs. It can tell a doctor, for example, exactly how much a patient's ultra-processed food intake, which is maybe being tracked via a meal logging app, is contributing to their liver disease risk compared to their baseline genetic risk.
Okay, that is definitely a step up.
It's incredibly powerful because it explains why two people with the exact same genetic risks might have completely diverging metabolic outcomes. Take the PNPL3 gene variant, which is strongly linked to fatty liver disease.
Right. Very common variant.
Yeah. A farm worker in Mexico and an office worker in Sweden might both have that exact same genetic variant. But the AI can isolate the variables to show that the office worker's sedentary lifestyle and environmental exposure are the actual triggers lighting the fuse. The AI is explaining the why by isolating the variables for the clinician.
Okay, isolating variables is helpful, I'll admit, but only if the original dataset accurately represents the patient sitting in the exam room. And that brings us to a massive systemic flaw in the data itself: algorithmic representation.
You're talking about bias.
Yes, these predictive models rely heavily on genomics and historical health data, but historically, the foundational data sets were trained almost entirely on Eurocentric populations. As a result, the algorithms systematically overpredicted risks for certain populations and entirely missed disease markers in non-Western phenotypes.
Right, the phenotype misses in early models.
Exactly. Take the South Asian thin fat phenotype as a perfect example. These are individuals who have a relatively low body mass index, or BMI, so they look quite thin, but they carry a very high concentration of visceral fat. That's the dangerous fat that wraps around the internal organs like the liver and pancreas, directly driving insulin resistance.
And the old models just missed it.
Completely. Older AI models were trained on Western BMI standards where risk is tightly correlated with overall body weight. They completely failed to flag these South Asian patients for metabolic syndrome. They were physically invisible to the algorithm. If we deploy these mathematically skewed tools globally, we don't just fail to help, we actively risk worsening health disparities by misallocating medical resources based on bad math.
I fully acknowledge that historical flaw. Early models definitely suffered from representation blind spots, and the consequences were very real. But it's vital to look at how the technology is actively self-correcting. We aren't relying on those older skewed models anymore. Look at how 23andMe's AI is currently refining polygenic risk scores.
Polygenic risk scores being the cumulative calculation of thousands of tiny genetic variants, right?
Right. They are now specifically engineering the algorithms to incorporate ancestry adjustments. This isn't just a minor tweak. It's biologically crucial. For example, African Americans face a 60% higher risk for type 2 diabetes, and that's heavily influenced by specific genetic variants like TCF7L2.
Which impairs insulin secretion, right?
Exactly. When glucose spikes, the pancreas struggles. By federating data across massive, diverse banks like the Pan-UK Biobank, Singapore's SG10K, and Brazil's 100,000 Genomes Project, developers are now training AI on 1.5 million highly diverse genomes. They are building the representation directly into the foundation.
Look, aggregating more diverse genomes is absolutely a necessary step. I won't deny that. But genetics alone don't dictate metabolic destiny. As you mentioned earlier, environmental factors are what pull the genetic trigger. You can have the TCF7L2 variant and never develop diabetes if your environment doesn't push your body into an inflammatory state.
Which is exactly why the cutting edge of AI is integrating multi-model data to solve this exact issue. Consider the landmark 2025 science paper. They detailed an ensemble model that blended those genetic risk scores with highly localized environmental data. They actually pulled air pollution metrics, specifically PM 2.5 particulate matter, from NASA's satellites.
Wow.
Yeah, and they combined that with exercise data pulled from wearable Fitbits.
Wait, why air pollution specifically?
Because fine particulate matter enters the bloodstream and triggers systemic oxidative stress, which makes human cells highly resistant to insulin. By combining the genetic baseline with the reality of the patient's environment, they boosted prediction accuracy by 25% for metabolic syndrome across highly diverse populations.
That's a massive jump.
It is. They successfully compared the predictive accuracy in heavily polluted urban India with the much cleaner air of rural Peru. And furthermore, developers are now using adversarial training. They literally train a secondary AI to challenge the primary algorithm, forcing it to ignore mathematically skewed proxies and focus purely on the biological and environmental markers that actually cause the disease. It ensures the model is statistically sound and medically accurate for everyone.
I mean, I appreciate the engineering ingenuity behind adversarial training, and blending satellite pollution data with genomic sequences is undeniably fascinating. But my concern remains stubbornly grounded in the structural realities we discussed earlier.
The infrastructure again.
Yes, you are describing a highly sophisticated, multi-layered data symphony. Genomics, satellite imagery, continuous wearable outputs, and flawless clinical history. That requires a level of infrastructural harmony that is incredibly rare. Yes, you can perfectly calibrate a model in a controlled, well-funded study in urban India or rural Peru. But deploying that seamlessly across the fragmented, underfunded, and wildly varying health systems of the globe, the systemic barriers to that kind of execution are immense.
They are immense, yes, but the trajectory of the technology is undeniable. We are witnessing an absolute paradigm shift in medical science. By integrating these massive data sets, the multi-omics, the real-time wearables, the complex genomic data, AI isn't replacing doctors. It is empowering them to act as super forecasters.
Super forecasters, I like that term.
Right? We are giving clinicians the ability to see the invisible cellular damage years before it becomes a clinical crisis. Gartner forecasts that AI integration will avert 50% of all metabolic disease burdens by 2030. That would drastically slash the World Health Organization's projected $1.7 trillion annual cost.
If it scales properly.
But the pilot successes are already operating in the real world. Israel's Clalit Health used AI to identify hidden prediabetics and cut actual hospitalizations by 30%. In Rwanda, a partnership combining AI with zipline drones is forecasting liver disease in vulnerable patients and delivering diagnostic tools directly to nomadic herders. We are conclusively moving from a medical system based on reactive firefighting to one of proactive, data-driven guardianship.
Well, I will certainly concede that the technological achievements are breathtaking. The ability of convolutional neural networks to analyze an ultrasound and detect fatty liver infiltration with 95% accuracy, which actually surpasses the diagnostic capabilities of human radiologists, is a remarkable feat of engineering.
It really is.
But the systemic infrastructural challenges remain largely unresolved. The persistent issues of the unexplainable black box, the lingering shadows of mathematically skewed training data, and the hard reality of infrastructural data silos all require rigorous validation and constant human oversight. We cannot simply declare AI the ultimate savior of global metabolic health until these models are fully transparent, clinically validated, and proven to work accurately across all populations, regardless of their local hardware.
And honestly, I think that is a vital point of convergence for both of us. AI is undoubtedly reshaping metabolic disease prediction from the ground up, providing insights we've literally never had before. But we clearly both agree that ensuring accurate representation and deploying transparent models, like the clinical validation standards outlined in the WHO's Global AI Initiative, are absolutely vital moving forward.
Absolutely.
It's not about just pushing the tech out. It's about ensuring it is medically accurate. The technology has to be guided by rigorous human validation.
Exactly. The predictive tools are only as effective as the infrastructural frameworks and the clinical trust that support them.
And as these data sets continue to balloon, I mean, we are looking at an estimated 10 billion connected wearables coming online by 2028. The predictive gaze of AI will only sharpen. With incredible innovations like quantum-enhanced machine learning simulating metabolic pathways down to the atomic scale, and gut microbiome sequencing entering the everyday clinic, there is so much more to explore in this material.
We're barely scratching the surface.
We truly are at the very beginning of this integration. It forces us to continually weigh the unprecedented predictive power of AI against the necessary practical cautions of its real-world implementation. The metabolic damage brewing inside millions of people is a silent, slow-moving storm. We finally have a technological radar that can see it gathering years before it hits. The question now is whether we can build the infrastructure to distribute that radar effectively and trust the warnings it gives us.